We'd like to start by acknowledging the Wadi Wadi people of the Dharawal Nation as the traditional custodians of the land where this project is based. We recognise country as more than land. It is a living, sentient system that encompasses the sky, waters, wind and all life, and has sustained Aboriginal communities for tens of thousands of years. We pay respects to elders past and present and emerging. As we consider how to generate cleaner energy, we reflect on Aboriginal knowledge systems that emphasise deep respect for country, using only what is needed, maintaining balance, and seeing energy not as a commodity, but as a relationship. This project is guided by those values.
This is our photovoltaic concept map, which displays our interconnecting ideas and thought processes for our proposal. At the very heart of our map is the theme of photovoltaic generation in Wollongong, our central concept, which is interlinked with various elements that implement solar energy solutions. One of our foundational elements is the Solar Resource Assessment, which discusses how much solar energy can be received, highlighting the importance of understanding Wollongong's solar irradiance levels to optimize solar potential. Moving on, we decided to examine the materials used in photovoltaic cells, such as monocrystalline, polycrystalline, and thin film, with monocrystalline offering the best efficiency for enhanced energy collection. The photovoltaic effect transports sunlight into energy, involving electron-hole pairs and the flow of electricity, ultimately leading to increased energy production. Additionally, we discussed design and efficiency considerations, including optimal tilt, shading, and seasonal changes, which were crucial for maximizing energy outputs. Seasonal factors like cloud extent and the sun's position we proposed would significantly influence energy yields, with summer providing the highest energy production compared to winter. Furthermore, system losses such as wiring, shading, temperature, and inverter efficiency were discussed, along with environmental aspects like land, people, water, and sky, which respect Aboriginal values and shared responsibility. This concept map was created as a guide to understand and optimize our proposal.
Wollongong's energy is connected to the grid maintained by Endeavour Energy. According to their website, Endeavour Energy is responsible for building, maintaining, and operating an electricity network that connects 2.7 million people to traditional and renewable sources in homes and businesses across Sydney's Greater West, the Blue Mountains, Southern Highlands, the Illawarra, and the South Coast. They're responsible for connecting hundreds of thousands of solar panels from private homes and businesses to the rest of the grid. Energy suppliers are a separate entity who generate the electricity and trade directly with Endeavour Energy, who distribute that power across their grid. The default retailer of electricity is Origin Energy. Origin Energy owns the Shoalhaven Hydro Pump, which is run by 2 hydropower stations at Kangaroo Valley and Bendiela. They also boast the Uranquinty gas power station near Wagga Wagga and the Araring coal-fired power station near Lake Macquarie. Energy Australia also generates electricity close to Wollongong. They own Tallawarra gas power station next to Lake Illawarra and the Mount Piper coal plant near Lithgow, northwest of the Blue Mountains. In Australia, about 15% of all electricity generation came from solar panels. 2/3 of that was from small-scale panels on top buildings, and only a third came from large-scale solar farms. Solar farms do not generate a massive amount of Australia's energy. A much larger contribution comes from individuals and families buying panels for their home. The largest operating solar farm in New South Wales is the Colan Valley Solar Farm, which has a maximum capacity of 150 megawatts. Most solar farms are government-funded community projects like the Colan Valley Solar Farm. Major energy suppliers to Endeavour Energy do not own any significant solar farms and instead prefer gas and coal power stations. Origin's soon-to-be shut down Araring Power Station generates a massive 2,900 megawatts, which is about 25% of New South Wales' total power requirements alone, and generates 20 times more energy than the largest solar farm in New South Wales. Here in Wollongong, about 24.5% of buildings and homes have solar panels, totaling to a maximum capacity of 19 megawatts. Wollongong has a warm, temperate climate, falling under Climate Zone 5 by the Australian Energy Regulator. Their data shows that our homes use the most electricity in winter and the least in spring, suggesting that our climate provides both cooling in the summer and heating in the winter. By extrapolating data from the graph and census data, we can find the total residential energy use. According to the 2021 census, Wollongong has about 20,000 private dwellings, with an average occupancy of 2.3 people per dwelling. From the graph, the total energy used in a year is about 5,000 kilowatt hours per year for a two-person home. This yearly rate, multiplied by the dwellings in Wollongong, is 106 gigawatt hours of energy used per year. Figure 1.5 graphs raw data from Endeavour Energy, plotting the energy use in North Wollongong over a 24-hour period. From the graph, you can see that the power usage is steady from morning to afternoon and peaks from 6 p.m. to 7 p.m. The off-peak hours range between 2 a.m. and 6 a.m. This graph gives a breakdown of the emissions released by different sectors in Wollongong. This information is sourced from Snapshot, who collect emissions data for council and community groups. The emissions are measured in tonnes of carbon dioxide equivalent. This unit standardizes the effect of different greenhouse gases on the climate into the equivalent effect that carbon dioxide has on the climate. From the pie chart, we can see that about 1/3 of our emissions come from sourcing electricity. Residential and commercial sectors have similar emissions at roughly 380,000 tonnes of carbon dioxide equivalent. A much larger amount of emissions comes from the electricity required to run Wollongong's industrial sector. By sourcing electricity through renewable means like solar panels, our emissions from burning coal and gas would be greatly reduced.
Photovoltaic energy is generated by converting sunlight directly into electricity by using semiconductors like silicon. This process is called the photovoltaic effect, and silicon is still the most commonly used material in solar panels. There are three main types of silicon used in PV cells. First, monocrystalline silicon is made from a single crystal structure. It offers the highest efficiency between 15 to 22%. It's perfect for rooftops where space is limited and is also quite efficient in low light conditions. Second, polycrystalline silicon, which is made from multiple crystal fragments, is slightly less efficient at 14 to 19%, but is more cost effective. And third, amorphous silicon, a type of thin film technology, is lightweight, flexible, and cheaper to produce, though its efficiency is lower, around 5 to 10%, and it tends to degrade faster over time. So how does it all work? When sunlight hits a silicon solar cell, photons with enough energy excite electrons to the conduction band, leaving behind holes. These electron-hole pairs are then separated by an internal electric field, creating a flow of electricity. This is the photovoltaic effect. The better we separate and collect these charges, the more energy that we can produce.
To assess the potential for photovoltaic generation in Wollongong, we must first consider solar irradiance, the amount of solar energy per unit area received at the Earth's surface. This includes visible light, ultraviolet, and near-infrared radiation. The national data from the Bureau of Meteorology shows that while Central and Northern Australia receive the highest levels of solar exposure, coastal areas in the south, including Wollongong, still experience moderate to high irradiance by global standards. This is due to our latitude at approximately 34 degrees south. However, coastal regions like Wollongong have greater moisture content and more frequent cloud coverage, which lowers average daily solar exposure compared to inland areas. The amount of solar energy reaching the ground is primarily influenced by two factors: sun angle and cloud cover. Wollongong's topography plays a key role in shaping solar potential. Nestled between the Tasman Sea and the steep Illawarra Escarpment, the region features a narrow coastal plain in the north and a broader one in the south. Flat or gently sloping areas such as the coastal plains are ideal for large-scale solar PV installations due to easier construction and better sun exposure. However, the escarpment and surrounding hills can introduce shading and reduce solar access in certain locations, especially during mornings and late afternoons. In terms of sunshine hours, coastal areas like Wollongong experience few brighter sunshine hours annually compared to inland areas. This is largely due to the moisture content and frequent cloud coverage, as previously mentioned, which temporarily lowers PV output during rainy or stormy conditions. This map shows the average cloud coverage across Australia at 9 a.m, and we can see that coastal areas like Wollongong tend to have higher levels of cloud cover. On average, Wollongong experiences about 5 to 6 octaves, meaning the sky is more than half covered with clouds most mornings. This frequent cloud coverage, along with areas typically high in humidity, can significantly reduce the amount of solar irradiance reaching solar panels. Less direct sunlight means lower energy generation during these periods, which is important to consider when planning and optimizing solar systems for this region. To maximize solar energy production, panel orientation and tilt are essential. For fixed solar systems in Wollongong, the optimal tilt angle is approximately 31 degrees, facing true north, aligning closely with our local latitude at 34 degrees south. Seasonal variation do influence output. Summer yields more energy due to longer daylight and fewer clouds, while winter sees a dip due to increased rainfall and shorter days. On average, Wollongong receives about 94 millimeters of rain per month and an annual maximum temperature of 21.3 degrees, both of which affect PV performance. An example of efficient solar design can be seen at the University of Wollongong Sustainable Building Research Centre, which hosts a 120-watt peak system split across 6 20-kilowatt peak systems arrays and a real-world demonstration of optimal panel placement and design.
One 350-watt rated panel has a kilowatt-hour rating of 0.7. For there to have the required estimated amount of energy needed for a household, we treat each as needing enough to support a 2 to 3 bedroom household. The average usage for a household is 14.1 kilowatt-hours per day if the house uses 5,150 kilowatt-hours per year. Therefore, we likely don't have the room for more than 13 panels, which would supply 9 kilowatt-hours per day, or 3,315 kilowatt-hours per year. From the 2021 census, we calculated 6,852 houses would need PV panels. The total amount produced from each household per year is 22.7 gigawatt-hours, and the required amount to supply the house per year is 35.3 gigawatt-hours. The implemented PV panels would make up 64% of the required energy, and the houses would need to only rely on other fuels for 36% of their energy.
So now we know that 35.3 gigawatt hours of energy is required to power the required 6,852 homes which are currently not powered by solar. But the problem is only 22.7 gigawatt hours of energy can actually be provided by the solar panels on the roofs of those homes. So if we take the difference of that, so 35.3 gigawatt hours minus 22.7 gigawatt hours, that leaves 12.6 gigawatt hours of energy, which has not yet been generated and is still required to meet the 35.3 gigawatt hour energy demand. Another thing we're going to take into account here is the fact that 13 panels will produce 3,315 kilowatt hours of energy every year, which means if you divide that by 13, that gives how much one panel generates every year, which is equal to roughly 255 kilowatt hours. Now that we know that 12.6 gigawatt hours of energy is still required to power the homes, and that 255 kilowatt hours of energy is produced by one solar panel every year, we can now find out how many solar panels are actually required to provide 12.6 gigawatt hours of energy, this required energy, which we can find by simply dividing 12.6 gigawatt hours by 255 kilowatt hours, the amount of energy produced by one solar panel every year, which gives us about 49,400 solar panels required to generate 12.6 gigawatt hours of energy. Now that we know how many solar panels are required, we can now find out the amount of land required for the solar panels to be on for things like a solar farm. But first, before we can calculate that, we actually need to know the area of a solar panel. And for a typical like 350 watt solar panel, which we base our calculations on, the dimensions of it are 1.7 meters in height by 1 meter in width. So multiply that by 1.7 meters by 1 meter, the height by the width, that gives 1.7 meters squared for every solar panel. So now that we know the area of it, we can then multiply that by the number of required solar panels. So 49,400 by 1.7 the area of a solar panel, and this will give us 83,980 meters squared of land for solar farms for these solar panels, which is equivalent to about 21 acres of land.
In 2021, there was a recorded 8.67 million tons of CO2 being emitted. 19% was electricity, and 6% of that was from residential households. By implementing the proposed idea, we can offset 64% of the energy consumed by houses yearly, which would reduce the 6% to 3.84% of electricity used by households, and reduce carbon emissions from 517,000 to 330,400.
In Aboriginal worldviews, energy is not just a physical resource. It is deeply connected to country and to the relationships between land, people, water, and sky. By choosing solar energy, we honour this interconnectedness. Solar is a clean, renewable source that respects the nature cycles and minimises harm to the country, designing systems efficiently. Avoiding shading, reducing waste, and maintaining equipment is a way of showing respect for the energy we receive. This approach reflects the principle of relationality. Energy is used in a shared responsibility that must benefit community and environment, not just individuals. Our proposal values energy as a living force, not just a utility. In doing so, it aligns with the Aboriginal concepts of respect, care, and balance with all parts of our country.